Hi, hello everyone. Good morning, good afternoon, and good evening to whichever part of the world you are. Welcome everyone to the today's session on essentials of explainable AI. This session is a part of our machine learning bootcamp, which we are doing in collaboration with AI Engineering YouTube channel by Srinivasan Srivatsan. And with that, let me introduce you all to our session speaker for today. It is Dipanjan Sarkar. And I'm sure most of you in the community must be knowing about him. And for those unattended, Dipanjan is a data science lead at Applied Materials. And he's also a Google developer expert in machine learning. He has delivered numerous expert sessions in the field of machine learning, deep learning, computer vision, and natural language processing. And he has been a mentor, author, and he keeps sharing and contributing to the community, and the kind of contributions he made to the data science community has been nothing but impressive. And he was also recently featured as a top 10 data scientist in India by a popular analytics magazine in India. And with that, let me welcome Dipanjan to the session. And Dipanjan, it's all yours now. And yeah, thank you for joining in.
Thanks a lot, Shanuk and DeFi for the invite. I think it's always a pleasure to be back again, sharing something interesting with the community. And yeah, I think thanks a lot, everyone, for making the time today. We will be covering some interesting aspects on explainable AI, as the session title says, and we will try to cut through the hype, discuss about the need and the importance of explainable AI, as well as look at some popular methodologies for being able to explain machine learning models. And also we will take a look at some hands-on tutorials, as well as we'll do a brief touch-up on how do you explain advanced models like deep learning models for computer vision, as well as natural language processing, that is text-based models, though we'll not go into too much in depth considering this is a machine learning focused session. So with that, I think I've already been introduced, so I won't spend too much time on this slide. But basically, I'm a data science lead, and I also am a Google developer expert in machine learning. I've written several books around machine learning, deep learning, as well as I have associations with various startups and companies in terms of their AI initiatives, as well as upskilling people in the field of artificial intelligence, machine learning, data science, and deep learning. Now let's dive into the session. So before we understand what is explainable AI, let's try to understand about the reason, or rather the necessity for explainable AI. So if I show you this simple image and I ask you, what do you see? You may not even need to think for a few seconds. It'll immediately come to your mind that these are bananas. Now you may think about that, why am I showing you a picture of bananas in the session for explainable AI? But let's continue and just take a look at where this leads to. So now if I show you this example, then you can see that on the left-hand side, we have probably green or unripe bananas, and on the right side, we have overripe bananas. So now if I show you these images, you'll see that, okay, these are like more diverse bananas in the form of overripe, normal, red, green, and so on. But these are all bananas at the end of the day. So the reason for showing this image is bias is something which is already ingrained in each and every one of our minds based on how we have been brought up, or the things we have been seeing on a daily basis, or rather the things we are consuming on a daily basis, and so on. So whenever we look at yellow bananas, we immediately think that that is bananas, but we often forget the wide variety of range of bananas. The same is with a rose. If I say that, have you seen a rose? The thing or the picture that will immediately pop to your mind is a red rose. But as you know, there are a wide variety of roses of a wide variety of colors. So the same inherent issues is also with the data itself, which we are feeding to our machine learning models. And that's where the inherent problem with machine learning is that, as you can see in this nice XKCD comic, which pretty much sums up what I'm trying to say in detail, that usually the process is that we have a bunch of data, we do some pre-processing, we do some transformation, we do some feature engineering, we dump our data through hundreds of models maybe, or tens of models, and then we pick up the best model and we check the performance and we say, okay, this is the best performing model with X% accuracy, precision, recall, R square, whatever be it. But the problem is that it becomes harder and harder to explain the decisions of why is the machine learning model making a certain prediction, or what is a step or a sequence of decisions which is leading the model to make a certain decision. And that's the whole reason of why explainable AI is becoming more and more important. Now, that is where, as I was saying before, that bias in the data leads to bias in machine learning models. Simple examples here could be sample bias, that is selective sampling of data. Like often, when we are working with tabular data, one of the key things which we will do is removing outliers. Now, if we are too strict with removing outliers, what can often happen is that we can remove, let's say, samples of data belonging to minority ethnicity and so on. And as you can see here in sample bias, what ends up happening is if we keep majority samples of well-off people and we remove samples, let's say, belonging to people who are not so well-off, and we train a loan lending model on top of this, what will end up happening is that if we use this model to predict that whether a person will be given a loan in the future, usually, let's say, people who are not having too high of an income, they will always get rejected by the model. So inherently, because of the bias in the data, the model itself becomes biased. Same with racial bias, as we know that if you intentionally or often unintentionally, depending on the skewness of your data, if you train on certain demographics of data like facial recognition, and I think some of you may have even seen in the news with regard to some of the newer GAN-based generative adversarial network-based models where people were trying to depixelize some images. And now, since the training data set was all based on Caucasian men or women, what happened is even if the pixelated face was that of a non-Caucasian person, it was ending up being translated to basically the picture of a Caucasian man. So that's where inherently racial bias creeps in. And same as with association bias, where due to the skewness of the data or due to lack of proper evaluation of fairness in the data, models end up giving preference to a specific culture or gender. One of the key examples has been AI in recruitment, which has affected Amazon a while back when they were using a resume screening model. In terms of measurement bias, we have seen this sometimes. Like, let's say if you're working on a Kaggle data set for medical imaging, you're predicting pneumonia, and the data set is of just one particular hospital. Let's say we get 98% precision. We are really happy with it, but is that sample representative enough across multiple hospitals? Maybe not. So that is where it may just perform well on one or two hospitals, but if you, let's say, pass in X-ray scans of a new hospital, maybe it will perform really poorly. So that's where measurement bias comes into play. And confirmation bias, which is something I think a lot of us just experienced. When we think of a banana or a rose, we indirectly or unconsciously end up thinking that it's a red rose or a yellow banana. But there are a wide variety of roses and bananas. The same is with the data. When we are making samples of data, we may unconsciously or sometimes consciously end up sampling and then modeling our data on that sample in such a way that it ends up being a biased data set and in turn a biased model. And the trouble with bias has basically plagued machine learning and deep learning systems since a long time. Obviously, the media will tend to over-sensationalize it, but the main thing you need to remember here is that you need to be very careful when you are looking at the news, and you need to think about the implications of this from a real world perspective. Like if you look at some of the news articles here, Amazon obviously had a resume screening algorithm which was trained on a biased data set. So it ended up basically discriminating and not selecting resumes which were belonging to women. Now, did they do it purposely? Not really. It was all because of not having enough due diligence when they were training on the data set and not checking maybe the implications of training on a biased data set, or even in the first place figuring out that the data set is biased. The same thing is with a lot of things in terms of computer vision based applications, facial recognition. annotation, tagging, object detection, and so on. And that's where, if you see some of the quotes from influential people in the field, be it from DeepMind or even Microsoft CEO, the main thing to remember here is that bias in the data is something which is very critical, and the errors in the systems propagate very quickly because of this inherent bias, because the downstream applications are ultimately being consumed by end users. So that is where we need to make sure that whenever we are training some model, we ensure that it's being trained based on a diverse source of data. There is enough representation with regard to different types of samples, be it race, be it religion, age, whatever be it, and to make sure that we try to debias our model as much as possible. And what are some of the implications of having bias in your data? One thing could be, like I said, if you're building a loan lending application or a loan lending model, and if you don't train it on a diverse set of data, you may end up having aspects like people who are not so well off may get rejected directly by the model. So that is one of the key implications of having sampling bias. Racial bias, this was an example which had plagued Google photo tagging systems a while back, though it's fixed now, where because the data set on which they had trained on was not diverse enough, and the proper diligence of tagging methodologies was not done correctly, they ended up tagging people of a certain race as gorillas, which is not really true. So that's where this was public facing, and this got like a huge blow up in the media and the news. But again, it's the fault is not inherently purposeful here, but the idea here is that when you're training a model, obviously you're dealing with thousands or maybe millions of annotation classes. So you have to do the due diligence before these kind of models go out publicly and are consumed by end users. Same thing here. If you search in any search engine with images of CEOs, usually you end up seeing more of images related to Caucasian rather than, let's say, a diverse set of images. And the whole reason is because the data set itself is skewed. So that is where the main challenge here always is, that unequal representation, gender stereotypes, like we in this set of images which get returned when you search for images of chief executive officers. So you rarely see any women here, but there are quite a few women CEOs who are doing pretty well. So that's where we need to ensure that even for simple search results, we need to make sure that the model is returning, or rather your retrieval system is returning images which are diverse enough. And another popular example of sample bias, so you have these facial recognition systems which are being used inherently in any new application across diverse domains, like let's say in taking images or photographs here. And as you can see, this is an image of a woman of Asian descent, and obviously it's showing did someone blink, because when the camera software was trained with the right kind of facial recognition, gaze correction, gaze detection algorithms, it wasn't trained on a diverse set of data. And hence it ends up thinking that someone is blinking here, which is not really the case. So you can imagine, like, if it's a toy project which you're building, okay, it's fine. I mean, we can think about, okay, these are the examples for which it doesn't work well, and you stop there. But if you are building an application, if you're building a software, or if you're ingraining a hardware inside a piece of software which will be consumed by millions across the globe, not just in one particular region, you can't afford to train a model on just one particular region's data, right? You have to think about having diverse sources of data from people or from data sources across the globe if it's going to be consumed by those people. And we have seen a lot of association bias which had come up some time back, where I think a lot of you might know about word embeddings. For those of you who don't know, word embeddings are basically a way of representing text in a numerical form, where an embedding is nothing but a fixed size vector. So using a vector of numbers, we can represent different words in an n-dimensional feature space. The beauty of word embeddings is because you have an n-dimensional feature space where you can represent every word by a bunch of numbers. You can kind of compare similarity between words, between documents, and so on. And that's where you can draw some kind of analogy here, like if man is to computer programmer, what is a woman most similar to? And what the model sometimes pops up as the output is homemaker, which shouldn't be the case, because it's not always true that each and every woman is just a homemaker. So the reason why this is happening is because the kind of data on which it was trained, maybe it saw a lot of instances where women was being mentioned in close association with homemaker. And these are kind of results from a standard word-to-vec model, which is kind of biased or being trained on biased data, where if you compute similarity that, okay, if a man is to computer programmer, what is woman most similar to? And you can see homemaker, housewife come up as the most important or the closest entities, which is not really always the case. Same thing with Mexicans, you end up seeing a lot of unnecessary entities here which shouldn't be really coming up. But the reason why this is happening is because it is being trained on data from the web. And as you know, data from the web can be inherently biased depending on the type of people who are typing that in or who are talking about it in online forums and so on. And the classic example of this was some time back, there was a online AI chatbot which was plugged into Twitter basically, and it automatically started learning from what people were commenting on its tweets, what people were writing when they were retweeting its tweets. And because there were no checks in the process, it ended up being like incredibly toxic within a day or so, and it had to be taken down. So what the kind of message from this is, you need to always remember that the models which you are training, it will be incredibly sensitive to the data you pass to it. So that is where you always have to be careful. And this is another classic example of Google Translate, and this is still present for some languages. Like if you see on the top left, we have the source text, he's a nurse and she's a doctor, which can be a valid reason or a valid case. And if you translate this to Turkish, you end up with this translation. And if you reverse translate it back, it ends up translating she's a nurse and he's a doctor. And the reason is because when it's using kind of like an encoder decoder model to do the reverse translation, it is switching the genders because based on its training data, it has been trained on a lot of instances where possibly it has seen sentences where nurse has been correlated with she and doctor has been correlated with he. And this is one of the most recent examples, again, where Apple Card had been accused of using sexist algorithms. So basically, the whole point of highlighting these issues is that it's not something which happened a few years back. It's even happening today. It has even happened in this year, and it continues to happen. So besides bias, there are other types of issues also, which is the reason why we need explainable AI and responsible AI, which I will come to in a moment. There are ways in which you can add noise to your data, but make it imperceptible to the human eye, but you can completely affect the underlying backend model's performance, which is being trained on this data, which is trying to predict on some new data. So if you can see here, we have a source image of a duck, we have a source image of a panda, we have a source audio signal like how are you, and we inject some undetectable white noise. And then you can get the target image here, which visually, or if you listen to it, it will look the same or sound the same. But if you pass this to the model, it will end up misclassifying it or completely predicting a wrong translation from the speech or the audio data. And this is the whole perspective of adversarial attacks, which is something I had covered a while back. The whole point here is that your model needs to not just make the prediction, but also explain which was the key region in the image or which was the key aspect of the audio spectrogram which led to the model making the prediction. Because if you deploy this in mission critical systems like something for tumor detection, where we are trying to see whether a tumor or a spot in the skin is basically malignant or benign, whether it has cancer or not. Imagine someone purposely sending an image with some noise injected to it. The model will vastly misclassify it as having cancer, but that is not the case. So these are real world implications where you not just need to just make some predictions with some probability, but also try to explain them. And that is what has led to the whole concept of responsible AI systems. And you will see this term cropping up again and again as you keep abreast with the latest trends in terms of machine learning, deep learning, and artificial intelligence. Responsible AI, the need for it is because, as we know, AI has a potentially disruptive impact. It has the capability to automate a lot of processes. Bias in the data can lead to bias in models. We have seen a lot of examples of this already. Relying completely on black box machine learning model decisions can lead to inherent problems. That is where we need proper human in the loop processes. And that is where we need to make sure we don't have a lack of control over model decisions. We shouldn't just blindly rely on the machine learning model decisions. And a lack of privacy and security. We just saw some examples where if you don't anonymize user data, or if you don't prevent or make the models robust to adversarial attacks, it could lead to disasters if they were breached with these kind of attacks from malicious users. And that is where most of the companies like Google, Microsoft, and so on have come up with a set of responsible AI principles. There are a lot of principles, but I've tried to summarize them into four major areas. One of the main components of saying that, okay, this is a responsible AI system is that it should be fair. So AI systems should be fair and inclusive to everyone. The next piece is what we will be talking about mostly in today's session, explainability. AI systems should be transferable. It should be transparent basically, which means that you should be able to clearly explain why is a certain decision being made by the model. Model should be accountable for all the decisions it makes, and in turn, it should be able to be trusted by the end users. The next thing is privacy. We need to make sure that we have regular regulations, and we make sure that if we are dealing with sensitive data, we don't expose it to the public. We keep it safe, and also we make sure that in case we are dealing with any kind of sensitive data and we are training a model on that, we should also make sure that the system is robust to threats and attacks, and it is not like this system can be easily breached. There are techniques like adversarial learning to make sure that models are inherently robust to noise, just like we saw earlier, where if you inject some white noise, the model performance can degrade. So these are the four main principles, but today's session, we will focus more on the principles of explainable AI. Now let's discuss about the scope and some of the key principles underlying explainable artificial intelligence. So the main perspective of explainable AI is like a regular process typically involves that, okay, you have some training data, you have a machine learning algorithm, you train it on your data, you end up with a learned function, which is your machine learning model, and you make some particular decisions and recommendations. And that is where questions may come up, that why is it making these decisions? So the whole point of explainable AI is to unbox this opacity of black box models. And why is it black box? If you're using a really complex model like a neural network, or let's say a complex ensemble model like gradient boosting or random forest, it becomes really difficult to explain collectively what were the decisions being made by thousands of decision trees. And that's where we need to look at a different perspective of using model agnostic methods to make these black box models as explainable or as white box as possible. And also make sure that by explainable AI, we don't just say explainable AI for the sake of it. And in the backend, we are internally just using a logistic regression model as our final model. We should be able to build more explainable models while maintaining a high level of performance. So we should be still able to use neural networks or boosting or wagging models, but we should still be able to explain the reasoning behind those models. And the whole point of explainable AI is to explain human users so that they can understand and trust the model decisions, and so that the model can stay fair and be accountable for all the decisions it makes. These are some of the key principles of an explainable AI system. Now, the definition of explainability or interpretability in XAI systems, there are three things: the what, the why, and the how. So by what, I mean what drives the model predictions. We should have the ability to find out that which are the features which are driving the decision-making policies of the model. What are the key feature distributions? And this ensures fairness of the model. We should be able to say that why did a model take a certain decision. So we should be able to discover and also justify that what were some of the key features and what were some of the values ranges pertaining to these features which were responsible to drive specific decisions or specific predictions being made by the model. And this ensures accountability and reliability of the model. And the third one is the how. So how can we trust model predictions? So this is where it is all about local or specific interpretation, where we should be able to take any data point. Like, let's say if a person is being rejected for a loan, we should be able to pick up that data point, all the features, all the values surrounding that data point, and we should be able to explain that why did the model take a certain decision on it. And this should be reproducible, and it should also be demonstrable, which means no matter how many times we show it, the end result of the interpretation should be the same. It shouldn't keep changing. And this would ensure transparency of the model, because you would be able to clearly show why is this model rejecting this person for a loan. And that is where the scope of model interpretation comes in, which is where you have two aspects. One is global interpretations, which is all about what are the key features which are affecting the model overall based on all the data instances which it has seen when it has been trained. And that is where it is about how to comprehend and interpret the whole model at once. So based on the feature space of the complete set of data instances on which the model has been trained on, what are the key factors, what are the key features which are driving model predictions. So that is known as global interpretation, also sometimes can be seen as global feature importance. And local interpretation is inherently the newer aspect in explainable AI, which is about understanding that, okay, if this person has been rejected for a loan, what is the reason behind it? Why did the model make specific decisions for a specific instance or a data point? And that is where we look at a neighborhood surrounding this instance and we try to explain the model decisions. And that is your scope, where global is looking at what the model has learned as a whole, and local is about trying to explain specific decisions based on specific data points. Now, let's discuss about traditional techniques for model interpretation. Model interpretation is something which is not really new. It has been there for quite a while. It's not like people have just been trying to explain model decisions in just the last couple of years. So before, we used to look at techniques like clustering our data, segmenting our data, reducing our feature space, visualizing our data in a lower number of dimensions, making model predictions, and then sorting the probabilities, building some lift and gain charts for those of you who may have done some analysis on this area, building decile profiles to look at which is the target segment of customers who is yielding the most returns. So that is where we relied on a lot of exploratory data analysis to try and explain model decisions. The other part is something which is still used in some sectors in the industry, like in banking and finance and so on, where there is a strict requirement that models need to be completely explainable. So you end up sacrificing performance there and going for some linear models like linear regression or logistic regression, or at the max you can go for a decision tree, not an ensemble model, by the way, a single decision tree model where you can easily explain the rules of these models. So that is where one thing is, okay, if I want a transparent model, what kind of models can I use out of the box? You can go for a linear model or a decision tree model. But the whole point of explainable AI is you should be able to use a more complex model, but it should still be transparent. And that's where we have this accuracy versus interpretability trade-off, where if you look at the graph here, the models on the bottom right, these are models which are really high in interpretability, like logistic regression, decision trees, and so on. But the problem is often you will notice that their accuracy is not as high as some of the newer, more nonlinear, complex models like ensemble models like gradient boosting, XGBoost, like GVM, random forest, or even neural networks for that matter. So there is inherently a trade-off, just like we have a bias variance trade-off in classical machine learning. Similarly, here we have this accuracy versus interpretability trade-off, that if we want to sacrifice performance, we can get inherently highly interpretable models. But if we want to go for a really high performing model, we may have to sacrifice the interpretability. So that is where explainable AI is trying to bridge the gap between these models, as in, even if I use these models, can I increase their interpretability by doing some kind of nonlinear approximations? And that is where we will now look at some explainable AI techniques and also a few examples, which will make things easier to understand as to how can we bridge that gap so that we can still use complex ensemble or nonlinear models, but we should still be able to explain them in a simple way to the end users. Now, considering structured data like tabular data, basically data from a database or an Excel or a CSV, I think most of you have worked on a data set like that. The main thing to remember here is that there are a wide variety of techniques. We will be focusing more on LIME and SHAP today for the purpose of this session, but I just wanted to give like a list of key techniques so all of you can at least do some key takeaways when you go back and revisit these when you dive deeper into explainable AI. So when you're looking at structured data, one of the key aspects could be using interpretable models directly, like linear models, decision trees, rule fit models. The other thing could be you could use interpretable models like decision trees or random forest, and you can look at the feature importances to say that, okay, these are the top features which are affecting the model performance. Then there are a set of methodologies which are known as partial dependence and individual conditional expectation plots, where what we try to do is we try to look at a range of values for a particular feature. Like, let's say we are trying to predict whether a person will not get a loan or whether they will get a loan, and we are looking at the feature age. So what we try to do is we look at ranges of ages. We try to vary these values of ages, and we try to keep the other features constant, and we try to see what is the effect on the model probability decision. In this way, we can build a partial dependence plot, which basically shows that, okay, if your age is increasing, the probability of getting a loan reduces. So that is where we try to use our model, and we try to build a dependency plot by comparing a single feature or sometimes two features with the outcome which we are trying to predict. The next thing is known as a surrogate model, where we try to take a black box model like, let's say, gradient boosting. We have our input features. We make the predictions using that model, and then we fit a proxy model or a simpler model on top of that model. So what I mean by that is we take the original input features, we take the predictions made by the XGBoost or the gradient boosting model, and we fit these predictions and the input features into a decision tree model. So essentially what we are trying to do is we are trying to substitute our XGBoost model with a simpler decision tree model, but we are still trying to model on the relationships between the prediction probabilities made by the XGBoost model and the input features. So that is where we are using this surrogate decision tree model to approximate the predictions of the underlying black box model as closely as possible while it is interpretable, because a base decision tree model is still interpretable rather than an XGBoost model, let's say, which has thousands of decision trees. But the two techniques which have seen a lot of success recently is LIME. One is LIME, which is known as local interpretable model agnostic explanation. So LIME tries to fit a local surrogate model around a neighborhood of data for a point which you're trying to explain using your predictive model. And the focus of LIME is to always explain how single prediction decisions were made. So here also it tries to fit a surrogate model, but instead of fitting a surrogate model across the complete data set, what it tries to do is it tries to fit a surrogate model on a local neighborhood. And we will look at some examples where LIME will become more clear. Now, the next part is Shapley values and Shapley additive explanations. So here, SHAP is a technique which was invented a few years back, but Shapley values have existed for decades. So what they're trying to do here is they're trying to explain again a model's output as a sum of effects of each and every feature being introduced into a conditional expectation. So what they try to do here is we try to take the features of our data set. We try to compute the importance of every feature by varying permutations and combinations of all the other features. And we try to see the effect of every individual feature there. And in that way, we can assign importances to each and every feature by treating our model as a black box model, because we don't care about the internal algorithm of the model, but all we care about is how the prediction probability is changing as we change the features with a combination of features using permutations and different orderings. And this will also be clear once we look at some examples. Now, LIME and SHAP are examples of model-agnostic additive feature attribution techniques. Now, additive feature attribution is the key underlying principle behind these models. The whole idea about this kind of an XAI system is that it can decompose a model prediction such that it is a linear sum of individual contribution of features. So at the end of the day, all we are trying to do is we are trying to decompose the model in such a way that we can explain it just like we explain a linear regression model with different coefficients. That's the whole perspective here, that can we reach to that stage by using some specific tricks so that we can even explain complex nonlinear models. Now, additive decomposition should work for complex nonlinear models, not just simple linear regression, so that it can be truly model agnostic. And by the way, model agnostic means model independent. No matter how complex your underlying model is, you should still be able to decompose it, and you should still be able to explain it in the form of how a combination of features is affecting the model prediction decisions. So just a bit of math. I'll try to keep the math to a minimal considering today's session, but some parts are essential. So just focus on the next few slides in a bit more detail. So if our model's objective function is nonlinear, then global decomposition is impossible. What I mean by that is you can't just decompose a model prediction using a linear sum of individual features, because your model itself is nonlinear. So that is where, if your objective function of your model is nonlinear, what you need to do then is to, like I said, use some tricks so that you can do some approximations. And that is where the focus is on local approximation of your model objective function around a sample of interest which you want to explain. So let's say a sample of interest, like let's say a person who has been denied a loan by the model. That is determined by I. What we want to do is we want to take that sample of interest, we want to take a neighborhood around that sample, and then we want to build a local approximation around our model decision function in that neighborhood. So that is why it is often known as a locally faithful model. And if you read the LIME paper, you will keep coming across this term, which says that we are not trying to build a global approximation model, but we are trying to just take a neighborhood around our sample of interest and build a surrogate model on top of that. So local interpretation focuses on interpreting or explaining a specific sample of interest. Okay, so we are not looking at explaining the decisions of thousands of samples of data in one shot. We are always looking at explaining a specific sample of interest at one point of time. That is one of the key things you need to remember. And the other perspective also, which is optional, not that it is always needed, is that if your original feature space X, which is basically all your features, if it's too complex, sometimes you can do a feature transformation before you do interpretation. So then the focus would lie on approximating your model decision function around a sample I with a linear approximation model G. So this is where the linear approximation model is also known as your local surrogate model, which is trying to explain the model decisions on sample I. And that is where you can use a simpler transformed feature space by making use of some kernels if needed. But again, this is optional. It depends on how complex your feature space is, like let's say if you're using word embeddings. Let's discuss a bit about the principles of LIME. So the whole perspective of LIME is that if we have a black box model, if we have some features and a prediction like why is a person getting flu, we should be able to say which are the key positive features and which are the key negative features which are affecting the model prediction decision. So as I said before, LIME focuses on training local surrogate models to explain individual predictions. We are not focusing on explaining thousands of predictions in one shot. We are always focusing on explaining the prediction decision of the model for one particular data point at a time. And LIME tests what happens to the predictions when you give variations of your data to the machine learning model. So the whole point here is that we look at all the features and we try to take different permutations and combinations of values of the features based on their ranges and their distributions. And we try to see how that affects the model prediction decision. And the reason for doing that is we want to figure out which are the influential features which are affecting the model probability the most. That is the whole point of doing this. And how do we do this variation? So what we do is we first decide that which is our point of interest, which we want to explain. And then we generate a new data set, which consists of perturbed samples and the corresponding model prediction. By perturbed sample, it is basically the variations of data points which we are creating around our point of interest. So this is also known as a neighborhood of perturbed samples. And the way of doing this is you could select data points around your point of interest. You could also vary the values of the features of data points around the point of interest by doing some averaging based on proximity points. And what LIME does then is it trains an interpretable model, which could be like a local surrogate model, like a linear regression or a logistic regression model. And how it trains it is it will train based on not just the data points which are being generated, but also by weighing each and every one of those samples by how close are those sampled instances to the point of interest. So that is where the proximity of the sampled instances to the point of interest becomes very important. And the learned model should be a good approximation of the black box machine learning model predictions when we are looking at it from a local perspective. Always remember that LIME focuses on local approximation. So we don't care about trying to explain things on a global level. We always try to explain things by looking at a specific data point and a neighborhood around it, and by building an interpretable local surrogate model on top of that local data point and the data points around it, which is going to be generated by some perturbations and variations. So the explanation model, which we will try to build using LIME for the point of interest X, is basically a model G, which is known as a local approximation model, could be a linear model, and that tries to minimize the loss L, as you can see here. So the whole point of the LIME objective function is known as L f g pi of x plus omega g. This is the mathematical definition of the LIME objective. And just to break this down in a simple way, our black box model is going to be the model F. Okay, so F is our original black box model, like let's say an XGBoost model. And what we are trying to do is we are trying to basically take a point of interest X, which we want to explain. We also take a neighborhood around that point of interest, which is known as pi of X, which is the proximity measure, which says how large of a neighborhood around the instance X we want to consider. We build a local model called G, which is a linear regression or any kind of a linear model around that local neighborhood, such that we minimize the loss. And we try to measure how close is our explanation to the prediction of the original model. Because when we are training this local model, we are not training it on the original labels. We are training it on the predictions which are being made by the original model. That is the key difference. So the LIME workflow, which will become simpler and simpler as we look through some examples also shortly, is that you start by training a black box model on your original data set, which could be like a complex nonlinear model, like let's say XGBoost. You choose your instance of interest or your point of interest for which you want to explain the predictions from the black box model. You perturb your data set, you generate variations from your data set so that you can generate some data points around the instance of interest based on a neighborhood around your data point of interest. you get black box model predictions for all these points. So based on that local neighborhood, you pass all those points through your black box model. You get your black box model predictions. Could be the probabilities, could be the predicted raw value. You weigh the samples by their proximity to the instance of interest. And this is basically the data point which we are trying to explain. And one way of assigning a weight could be, let's say, simplest example could be Euclidean distance. But in this case, one of the popular methods which is used by the LIME model is known as an exponential smoothing kernel. So we use a exponential smoothing kernel transform to give a weightage to each and every point as to how close they are to the point we want to explain. Then we fit a weighted interpretable linear approximation model. So this is basically a surrogate model, which is like a linear regression model, which we fit on this local data set with the variations. And then we explain the predictions by looking at the coefficients of this local model. So at the end of the day, LIME is trying to fit a local surrogate model on the predictions of the black box model at a particular neighborhood. A simple example on tabular data could be this, where we have some data points. Let's say we have two features just to keep things simple. So the figure A you see here is the original black box model, which is a random forest model with a decision boundary for binary classification. So let's say the blue is class 0 and the gray is class 1. So it is able to detect complex nonlinear patterns between two features and separate out the boundaries. Now what we do next is we select a point of interest which we want to explain, and we generate a neighborhood around it in the form of that, okay, we want to take, let's say, 100 samples around my point of interest. And we select these samples, could be from the original data points, could be from some kind of approximations also from your original data points. And then you use a kernel function like Euclidean distance or exponential smoothing to give weightage to each and every one of these samples around the point of interest. So that's why you can see that the points closer to the point of interest are given higher importance and the points farther away are given lower importance. And then you train a local linear approximation model on top of this, like a logistic regression model, and generate a local decision boundary. So you can see that the true decision boundary is like this, but when we are just considering explaining this data point, we don't care about the full decision boundary. All we care about is the neighborhood around it. And that is where we generate a decision boundary that if it's on the right side of this boundary, it belongs to the negative class. If it's on the left side, it belongs to the positive class. And then we generate interpretations from this local approximation model. That's the whole perspective of LIME. So LIME on text data. So in terms of natural language processing, as you know, one way to represent data is every word becomes a feature, and the value of the feature is basically the number of times that feature or that word is occurring in a sentence, or could be an association, whether a word is occurring or not occurring. So if you want to explain a text model, like let's say naive Bayes or logistic regression, let's say we want to explain if email content is spam or not. So what we do is we select the data point of interest. In this case, it is this comment or this email content saying, for Christmas song, visit my channel. So let's say this is like a YouTube comment which is coming into any channel. And this has been tagged as spam. So we want to explain why did the model say that this is a spam comment. So what we do is we generate perturb samples around the point of interest, where every row is a variation or a perturbation. So how do we do that? You can see here that we are considering different combination of features with the values being turned on or off, which means whether they are present or not. And we are trying to see what is the effect on the overall model. So these probabilities, by the way, show the predicted probability of spam for each of these sentence variations. So what that means is we take all our unique features for Christmas song, visit my channel, and then the emoji. We generate different combinations with ones or zeros that whether they are present or not. And we pass these feature vectors through our already trained, let's say, naive Bayes model, and we get the probability. And the reason for doing that is we want to see what is the black box model predictions and how are each of these features influencing the model prediction probabilities. So that is where the probability column shows the black box model predicted probability of spam for these features for variations of our original sentence. And the weight column basically shows the proximity of the variation to the original sentence, which can be calculated in this case as 1 minus the proportion of words that were removed. So this is like a weightage being assigned to each of these instances. And then what we do is we train a local approximation model, like let's say logistic regression model, to generate a local decision boundary on this. And then once we do that, we can easily get the coefficients from that linear model, and we can see that channel ends up having a really high feature weight. And you can clearly see the reason behind it. If you see these two variations where channel is 1, the black box model probability is really high. But if you see for some other instance, like let's say Christmas is 1, probability is low, Christmas is 0, probability is still very low, which means basically the word Christmas is not really contributing that much to the black box model prediction decision. So this is where, by making various variations in the feature values and fitting a local model on top of these variations and the underlying black box model prediction, we can approximate the decisions being made by the complex black box model, even if this is a neural network, and be able to explain in the form of simple coefficients from a surrogate model. That is the whole point of LIME. And the same thing in the form of image data. So LIME can even be used on image data, where if you have the original image here, which is a funny image of a Labrador playing a guitar, you can see that if the model predicts electric guitar, the LIME model can show a patch of pixels, also known as superpixels, to say that which is the region of the image which contributed the most to the model making that decision. And that is where we don't perturb individual pixels, because the variations could be huge. We end up basically segmenting the image into groups of pixels and turning them off or on. And then we try to see how is it affecting the model prediction decisions? How is it affecting the model probability? So in this way, we can look at regions of the image, and we can try to explain that which is a region of image which led to the model having the highest probability for a specific class. Now coming to the next technique, which is all about SHAP. So SHAP underlying principles include using Shapley values. Shapley values was invented by Lloyd Shapley, and this is not a new concept. So Shapley values is basically a method for assigning payouts to players depending on the contribution towards the total payout. This is like a principle from game theory, which is slightly complex, but let us look at it from some simple instances and even some examples shortly. So what players try to do here is they try to operate in a coalition, which means they try to operate using cooperation among each other, and they try to obtain a certain gain from that cooperation. So in our case, the game itself is the prediction task for a single instance of the data set. Remember, for all these techniques, we are trying to explain why did the model take a specific decision. And the gain here is the actual prediction which the model is making minus the average prediction across all the instances. So the average prediction across all the instances is whatever is the model prediction for all the instances divided by the number of samples. And then we have an actual prediction for a local instance. And the gain is basically actual prediction minus the average prediction. And the players involved in this game is basically all the features which are kind of interacting with each other, which are collaborating with each other to make the model make that final prediction decision. And the Shapley value of a feature is the average marginal contribution of a particular feature over all possible coalitions. And what I mean by that is, considering all possible combination of other features, what is the effect of a specific feature on the model prediction decision? That is known as the Shapley value. And let's look at this through an example. This is a classic example given in Christopher Molnar's Interpretable machine learning book. I would definitely recommend you to check out this reference later on also. But let's say we are trying to predict that if we have a house in a particular place where the house is on the second floor, square feet area is 50 meters square, it's nearby a park, no pets are allowed, then let's say the price is 300,000. Now the goal is to explain how each of these feature values contributed to the prediction. So that is where, let's say we have 1,000 such houses, and the average prediction of our black box model for all these 1,000 houses is 310,000. Okay, 310K. So now let's say we are having a combination of these features for a particular house. So we can say that the feature values that a park nearby, cat is banned or not, area is 50 square feet or not, and second floor, they worked together in a coalition. Okay, they interacted with each other to achieve this final prediction of the model of 300,000. So far, I think it is clear. We are just trying to set the stage as to what did the model look at to make the prediction. Now, the goal of Shapley value is to explain the difference between the actual prediction made by the model for this local instance versus the average prediction across all the instances, which is basically in this case a difference of 10,000. So one way of explaining this could be that the park nearby contributed to 30,000, size 50 contributed to 10,000, flow second contributed 0, and cat band contributed minus 50,000. So if you combine all of these values, it ends up to minus 10,000, which is the final gain of the model. And the gain is the actual prediction minus the average prediction across all the instances. So how do we come to this final explanation? How do we come to this final explanation? This is just one possible answer. There could be n possible answers. So that is where we try to look at all those n possible combinations. A Shapley value, like I said before, is the average marginal contribution of a feature value across all possible coalitions, which means all possible types of feature interactions and combination of features. So let's just look at what is the contribution of the cat being allowed or not as a feature, and how is it affecting the model. So how do we get the Shapley value or the coefficient for that feature? So let's say the coalition or the feature interactions we are considering is whether a park is nearby or not, and whether the size of the house is 50 square feet, let's say. So those are the two feature interactions of the coalition which we want to explore, and we want to try to explain the importance of the cat band feature. So here we simulate that these are the three features which are interacting with each other. They are in a coalition. Now, if you remember, we are not considering the feature called second floor apartment. So that is where, if we are not considering that feature, we still need to include it, because a model, you can't just drop a feature, right? Then it will say dimension mismatch. So that is where, for the feature which we are not considering, you just replace it by the value from a randomly drawn data point which is near to that point. And let's say in this case, we drew a data point which had the first floor as the instance value in that data point. So the second floor value, that is why, gets replaced by first floor, because this is a random value which is drawn from a nearby data point. Because we are not bothered about this feature, we want to measure the effect of how these two features are interacting with whether a cat is present or not. And then we predict the price of the apartment with this combination. So we start off with a cat is not allowed, park is nearby to the house, size of the house 50 square feet, and we don't consider the floor, so we just substitute it with a random value, and we predict that, okay, it's 310,000. So this is where what we do is we then remove cat ban from the coalition and we replace it with cat is allowed. And then we try to see that, okay, with the same combination of features, if a cat is allowed, how is it affecting the overall prediction? And we see that it becomes 320,000. So the contribution of cat band ends up becoming not present minus present and the feature interaction, and it becomes minus 10,000. So the estimate depends on the value of the randomly drawn apartment that served as the donor for the cat and floor feature values. So what happens here is we had just two combinations here, whether the cat is present or not, but we could vary these values also. We could also try out whether it is near a park or not near a park, whether the square feet is 50 or not 50, or maybe whether it's 100, 150. So that is where we can try different variations of these features in the coalition, and we can check the effect whether cat is present or not present, and we can average the contributions across all these instances. And that is how you get the Shapley value, by averaging the contribution of the feature across all possible coalitions. So this is where if we had different features like park is nearby or not, square feet of the house, the floor of the house, and so on, you could have all these type of combinations, as you can see. One is whether cat is present or not by itself. You estimate the probability of the model or the prediction value of the model. You then consider whether a park is nearby or not, whether the size of the house is 50 square feet or not, whether the floor is second floor or not, and then you start combining multiple features. And for each of these combinations, we compute the predicted apartment price with and without whether a cat is allowed or not. And you then take the overall difference, or rather in this case, you take the overall weighted average to get the final marginal contribution. And this is how, by doing various permutations and combinations of features and feature values, you try to get the Shapley value, or rather in this case, it ends up being a measure of importance of each and every feature to the overall model. So that is where you can see we are not treating this feature in isolation. We are treating this feature in combination with all the other features when we are trying to explain the model. And that is where SHAP stands for Shapley Additive Explanation. It is an enhancement on these Shapley values. It assigns every feature an importance value for a particular prediction, and it tries to explain the output of the model as a sum of effects of every feature being introduced into a conditional explanation. And remember, all these things which we are getting will always be from the black box model. We are not doing any local approximation here yet. All we are trying to do here is we are using that black box model, and we are trying to vary the feature values and get the predictions, and then we are trying to see how much is the effect of those predictions. So that is where SHAP tries to explain the output of your black box model as a sum of effect of features being introduced into a conditional expectation. So as we start introducing features, how is the model prediction changing? Whether it's increasing, decreasing as we keep introducing feature. And the SHAP values result from averaging over all possible orderings. Okay, that is the most important thing to remember, that the order matters. A simple example could be, let's say we have this really nice example from the creator of SHAP himself, Scott Lundberg. You can check out this video for more details later on. But let's say you have a black box model, which could be any possible model, any possible nonlinear model, and you pass the features related to a bank customer, John, and the model says that there's a 22% chance that John will have repayment problems, and we don't give the loan to them. So now the question comes, what was the reason behind it? And that is where we first take a look at what is the average prediction of the model across all bank customers. Let's say that is 16%. And the prediction for John is 22%. So SHAP tries to explain what is the reason behind this gain, or in some cases, what is the reason behind this loss. And that is where we start off with the base rate, which is just like an intercept in a linear model, right? We go with the initial base rate, which is 16%, which is predicted on an average. And then we add in the first feature that, okay, John's income is not verified. And remember, as I said, SHAP is based on conditional expectations. So given that income is not verified, how does the probability or the expectation change? So from 16, it bumps up to 18.2%. Now, considering theta 1 is already there or x1 is already there, introduce x2. So now when you introduce the second feature to the mix, debt to income ratio is 30. Probability of the loan repayment problem rises up to 21%. Okay, so now it gets bumped up. Then you add in another feature that bank account was delinquent 10 months ago, which is a big problem. And now it gets bumped up to 22.5% from 21%. So you can see we are basically taking a combination of features, and we are trying to say that given some features have already been introduced into the mix, how is the overall expectation or the probability or the raw value you're predicting changing? Then we introduce another new feature that, okay, no recent account openings, and that bumps the probability down to 18.5%. And then we have another feature, 46 years of credit history, that bumps it up to 22%. So considering all these features being introduced in this mix, we end up getting the explanation of these coefficients for the final prediction. And by the way, how are these being computed? These are being computed from the Shapley values, which we just saw here, where You try to take every feature, you try to vary all the other features, and you try to see the effect of each and every one of those features. So underlying values being used by SHAP are the Shapley values. Now, the main thing to remember here is that we introduce these features in a specific order here. So if you change the order, let's say instead of 46 years of credit history being introduced in the 5th position, if you introduced it in the uh, 4th position here, then you can see that the coefficients change because the order matters in case of SHAP when you change the order of the features, because you're considering a conditional expectation always. So that is where the order matters in this case. And that is why the coefficients which you assign, or the importance of the values which you will assign to each and every one of those features, you can't just take it based on one order. You have to take it from averaging over all n factorial possible orderings. So you have to take a permutation of each and every one of the features, considering all the other features are present, by permuting those features also. And that is where you get the final feature importances or the Shapley values for each and every feature by averaging over all n factorial possible orderings. That is the key principle of SHAP. You don't just take one sequence of features being introduced into a conditional expectation. It is the marginal average over all n factorial possible orderings. This is something you should keep in mind. Now let's take a look at some standard examples of explainable AI. As to, we have learned a lot about the concepts, but how do these things really look in practice? So let's say we are trying to predict the house prices. So a standard model would say, okay, we have learned based on our training data, you give us a new house, and I will say that, okay, the price of the house is $699, but what is the reason behind it? So that is where we will try to use SHAP as an explainable interface on top of our black box model. So let's say this is our house price prediction data set. It is a standard data set for Boston house prices. We have a lot of different features, like what is the crime rate, what is the pupil teacher ratio in schools, what is the percentage of lower status population near the house, and so on, number of rooms in the house. So a wide variety of features are there. Now we want to build a model on this, a regression model, and we want to explain the prediction of why a model is predicting the house price as a certain value. And that is where we will use SHAP as our XAI interface on top of our black box model. So when you build a SHAP model on top of our black box model, we can get artifacts like this. So you can get a global feature importance no matter what your model is, even if it's a neural network model. And by the way, these values are basically the average SHAP values for the features across all the data points. And you can see from here that the top features which are driving house prices up globally include the percentage of the lower status of the population, average number of rooms per dwelling, pupil-teacher ratio by the town, and many other features. And now what you can do is you can also look at the partial dependencies. So this is based on what the model predicts for each and every one of the data points which are passed to it. And you can overall get the idea that if I have a higher percentage of lower status population around my house, the overall prices of the house slowly start coming down. If I end up having a higher number of rooms, the prices of the house start going up. And if I have a high pupil teacher ratio per school, that means maybe those schools are not, I mean, there's a lot of workload on the teachers in those schools, and that is why maybe the housing district is not as affluent as other areas, so the prices go down. And then you can go for local interpretation that, okay, if the actual house price was 12.7 in thousands of dollars and my model predicted quite close to it, if you see 13.4, what are the key features which led to the model making those prediction decisions? And you can start getting artifacts like this, that LSTAT, RM, PT ratio, these were the key indicators which are driving the house prices down from the base value, which is 22.53. And this is the base value across all possible houses, the average value which we are getting from the prediction. And you can say that the house price is 13,481 because LSTAT is 22.6, RM is 5.71, PT ratio is 21. You can give a simpler human explanation also to make things easy to understand, that house price is this because of a higher percentage in lower status population, lower number of rooms on an average, and a high pupil teacher ratio. Similarly, if you have a house with a higher price, you can see that the explanations change accordingly. And you can then explain that the house price is $47K because the number of rooms on average is pretty high, lower percentage in the lower status population, which means it is probably in a highly priced location. And also the house is at a shorter distance to the major employment centers in Boston, which means it is pretty well located. So these are the key reasons why the price of the house is higher and why is the model predicting that. So you can use these explanations to explain specific model decisions. And similarly, you have other types of problems also, like if I want to predict whether a person is earning more than $50,000 or not, you can fit this kind of data again through once you build a black box classification model, you can fit it through an XAI interface. And you can get features like if a person is married, the age of the person, capital gain of the person, the education qualifications of the person. These are the key factors which are driving the model to say that whether a person will earn more than $50,000 or not. And you can get these kind of partial dependence plots, and you can draw some conclusion also that a married person has a higher income on average. That is what the model has seen from the given data points. A middle-aged person typically ends up having a higher income, as you can see in this bracket of age. Higher educational qualifications lead to a higher income, and similarly, higher capital gain leads to basically a higher income. So you can start seeing these kind of relationships in your data. And you can also explain why is the model predicting that a person's income is less than $50,000, or let's say if a person's income is more than $50,000, you can pick up specific data points of interest and you can explain that, okay, this person is in a clerical position, no capital gain, not married, pretty young. But in this case, they are in a special profession. Their age is 51, pretty high educational qualification. They are married. So probably these are the reasons driving the model to say that they are earning more. Now, considering this is more of a machine learning session, I won't go into too much detail for the deep learning aspects, but you can interpret deep learning models on image data where you have different types of techniques, like you can look at activation layers, you can look at SHAP values from the gradients of the convolution neural networks. You can hide different parts of the image and look at the model prediction confidence. This is something we saw in the LIME example, if you remember, where we were hiding parts of the image and seeing the model prediction confidence. And we can look at the gradient class activation maps. So just to kind of look at how some of these things look like a typical convolution network has multiple layers and it tries to predict whether an image belongs to a particular class. So you have convolution layers which focus on feature extraction, and pooling layers which downsample the extracted feature maps to reduce overfitting and enhance features of certain parts of those images, the base images. So without going into too much details about CNN, I just want to show you some visual examples so you get a feel for how explainable AI can be used for images. So a classic example is explaining why is a model predicting a pullover image as a pullover, right? Or a shoe image as a sneaker. So that is where what we can do is we can look at some of the feature maps from the convolution neural network to look at that, okay, because the edges here are belonging to the handle of the handbag, belonging to the edges of this handbag, probably that is the reason why the model is ending up predicting this image as a handbag by looking at these edges, looking at the texture, and focusing on the handles of the handbag. You can also look at various feature maps from the convolution filters, which are basically internal to the CNN model. Like you can extract specific parts of the neural network model, and you can see that if I take filter number 13, which is, let's say, in a particular layer in the neural network model, you will end up seeing that, okay, when I'm passing an ankle boot image, it is easily able to recognize the edges of this ankle boot and it can predict it with a high confidence. But if I pass the image of a trouser in that same layer in the neural network, in that same filter, it is not able to activate anything. But if I look at a different layer or a different filter in the same layer, a different convolution filter, it is easily able to outline the edges of the trouser. and the shape of the trouser. So that is where, by looking at different regions of the neural network and trying to visualize what it sees as you pass different images, and by looking at the class probability, you can say that filter number 3 for the neural network really is very influential, and the trouser prediction probability really rises up high whenever I am passing a trouser image, and this is the reasoning behind it, that this part of the network gets activated. Similarly, this part of the network gets activated when I'm passing images of shoes. So these are some preliminary ways in which you can explain your neural network model, but it becomes very difficult because you need to look at each and every layer and each and every filter in your neural network. So that is where you can look at SHAP gradient explainer, which assigns SHAP values which are positive, which increase the probability of a class you're trying to predict. And if it assigns negative SHAP values, they are represented by blue pixels, which reduce the probability of the predicted class. And if you have some sample images here and you pass it through any deep learning model, it will give you some prediction probabilities. And you can see that the first most probable prediction is a great gray owl, which focuses on the facial structure and texture of the image. Second most confident prediction is a prairie chicken, which focuses more on the eyes of the image rather than the overall facial structure. Same with the second image. When the model is predicting it as a desktop computer, it is looking at this part. The person is completely ignored. But when it's just looking at the screen, you can see that this keyboard and the mouse region, which were highlighted here, they are being ignored here. And similarly, for the Egyptian cat, it focuses on the overall structure and the texture. But for a tabby cat, when it's predicting it as that, it focuses on only the facial texture and the pattern. So by using techniques like this, you can explain which parts of the image are being highlighted and influential for the model making the decision for a particular class. And there is GradCam, which looks at the gradient class activation feature maps. And you end up getting something like this, where when you're predicting a dog, it will highlight using a heat map, which is the region of the image which is the most influential for the model to predict the class as a dog. Or if I'm predicting it as a cat, which part of the image is most influential. So these are some techniques you can use for image data. And for text data, we discussed LIME, where you saw an example of how we changed the feature values and the variations of it and try to see the feature importances. Similarly, you can use SHAP also. And let's say we have a simple sentiment analysis problem where we are trying to predict that whether a particular reviewer has given a positive or a negative review for a movie. We can look at instances like this using our SHAP model interface, that which are the features which are affecting the model in a positive or negative way. And you can see words like worst, bad. They are basically reducing the effect of the model and to predict it as a positive class. And that is where you can also look at words like excellent, great, which are basically influencing the model to make prediction decisions in the positive direction, which means predict the class as positive or the sentiment as positive. And you can make local interpretations also, like which are the features driving the model to predict a negative sentiment. So if this is a movie review and our model is predicting it as negative, you can get coefficients assigned to each of these words. And we saw this example in LIME, right, where we saw how each of those features were being assigned coefficients. And you can say that which were the reasons which led to the model to predict that this is a negative review. And similarly, which were the key influential words which led to the model to predict that this is a positive review. So we are running out of time. I will quickly show you how you can get some of these plots in SHAP to start with, and then we'll try to see if we have some time for LIME before we wrap up the session. We will take a simple machine learning model example, given that this bootcamp is focusing on machine learning rather than looking at deep learning. Maybe we will do a deep learning session as a follow-up sometime. So let me quickly try to get to this notebook. So we will start with a simple example. That same house price example we saw earlier, we will try to look at that. And this is where we have that same data set. If you remember, we have all our features related to those house prices, where we have the crime, distance from the Boston main employment centers, PT ratio, percentage of low status population. These are our prices in thousands of dollars. And then we do a simple train test split. We fit an XGBoost regression model on our training data. We make predictions on our test data, and we see that overall explained variation is 90%, R squared is 90%, which is pretty good, but we don't care about performance right now. We want to explain using SHAP. So you can install SHAP using pip install SHAP. That will install the package for you. And then what you can do is you can use the tree explainer object from SHAP, pass in your black box model, pass in your train data. This will create an explainer instance. And then you explain or generate the SHAP values for your test instances. So if you look at the SHAP values, you will get these kind of coefficients for each and every feature. And these are basically the instances of the Shapley values, which we saw earlier, right? Which kind of assigns coefficients or importances to each and every feature as to how they are affecting a local prediction decision. So when we visualize those feature importance values, you remember, if we want to visualize the global feature importance, we will just average the feature importance or the Shapley values across all the data points and compute the global feature importance. When we want to explain that, okay, why is the house price for this house, let's say $20,000, we will look at these Shapley values and show the effect of that. And that is what we will do next. If you plot the summary plot, it will just average the Shapley values across all the features, across all the data points, and it will show you that LSTAT, RM, PT ratio, most influential features. And I think we saw this earlier also when we looked at the presentation from before. So using the summary plot function, passing in the SHAP values, your actual X test data, you will be able to generate this global feature importance plot. And then let's say we have a house price which is $21,500. Our model is predicting pretty close, $20,300. And the average prediction across all the data points is $22,500. So we want to say that what is the reason for the model's gain, or rather in this case loss, that it's ending up predicting $20,300. And that is where you can call the force plot function, pass in the average value, which is 22.58, the base value across all possible model predictions, pass in the SHAP values for data point or house number 10, and pass in the features for house number 10. And you can see it clearly says that, okay, these were the most important features, that percentage of lower status population is pretty high, number of rooms are around 5.9 on an average, and age of the house is pretty large. These were the main reasons for the house price to slowly come to the negative side or slowly drop. And similarly, for a house price which is slightly higher, around $32,000, we can generate a similar plot, and you can see that age of this house is much lower, percentage of low status population much lower, number of rooms is higher. So these were the most influential features in driving the house price higher than the base value. So that is exactly what SHAP does. It gives us the specific explanations as to why did the model say that the house price is $31,000. And you can plot similarly the feature like the partial dependence plots, where we discussed this earlier, right? That increasing the lower status of the population drops the house prices, number of rooms, PT ratio. So I'm not covering these due to the interest of time, but it's basically what we just discussed earlier in the presentation. Similarly, you can do the same for classification. Let's say we convert our regression problem into a classification problem, where if the prices of the houses are more than $30,000, it is a high-priced house, and if it's less than $30,000, it's a low-priced house. So we convert it into a simple binary classification problem. Now we train a really complex XGBoost classification model on top of this, and we end up getting a pretty good performance. Overall, we're able to predict 89 houses correctly as low priced and 8 houses correctly as high priced out of 11 high priced houses. And then we want to explain the prediction decision. So you can just plug in that same XGBoost model again with the training data, create an explainer instance, and then you can generate the SHAP values for each and every instance of your test data. And these basically become your coefficients using which you can explain which are the key influential features affecting the model prediction decisions. And in this case, also you can generate those kind of feature importances. And you can see for the classification model, the distance to the main employment centers in Boston area become one of the more important features. And then you can generate simple prediction values again, that if the base value is minus 4.3, base Shapley value, average Shapley value, why is this house priced much lower? And you can see that percentage of lower status population, again, pretty high. Number of rooms on an average is 5.9. So these kind of features, again, are driving the model to predict the house price as a low priced house. And similarly, for a high priced house, we can see the clear difference between these two and compare, and also get the understanding as to why the model is predicting these kind of instances. Okay, and coming to LIME, for LIME, what you can do is, let's say we have that census income data set we saw earlier, where we were trying to predict whether a person's income is more than $50,000 or not by looking at a wide variety of features, like what is the occupation of the person, whether they are married or not, educational qualifications, which country they are from. So in this case, we can basically do a get dummies to convert our categorical data and then build a classification model, in this case an XGBoost model. And then we want to explain why is the prediction decisions of this model saying that whether a person is earning more than $50,000 or less than $50,000. So that is where you can use the LIME package by default, or you can even install the Skater package. That is also an open source package which gives you LIME under the hood. And you can create basically an interpretation object by passing in your X-train, your Y-train, your feature list, and then you pass in your model, just like we did the explainer instance in case of SHAP. Here you create an in-memory model instance by passing in the model and the features. And then you can get the feature importances again, that okay, if they are married, their age, their educational qualifications just become the most important features which are affecting the model prediction decisions. You can generate partial dependence plots again, where if the capital gain increases, the probability to predict probability to predict whether they will earn more than $50,000 or not increases. Middle-aged people end up having a higher probability to earn more. Similarly, higher educational qualification increases the model prediction decision that the person will earn more, and so on and so forth, with different kind of interactions and prediction decisions. And you can use LIME to explain that, okay, if the person is earning less than $50,000, you can use the LIME tabular explainer instance, which is available also in the base LIME package. And you can get these kind of decisions, which we saw earlier in the slides, if you remember, that if the capital gain of the person is 0, if they are basically not married, and also if their age is 27, those are ending up being influential features to affect the model prediction decisions. And similarly, in this case, features like they are married, educational qualification is high, these kind of decisions end up predicting the model decisions as the most influential decisions, which are affecting the final model prediction. And of course, the problem here always remains that the more number of categorical features you have, they start affecting the model predictions decisions, especially with the neighborhood. So you will end up seeing features like this, which will always come up. And that is where the neighborhood is always important in case of LIME, which is kind of like a hyperparameter, which you may have to play around with to get a consistent decision. So that is why I always advise to use SHAP instead of LIME. It is a much better technique, which is more robust, and it is not dependent on the neighborhood. It is dependent on is the conditional expectation and averaging across all possible conditional expectations by considering permutation and combination of features. Okay, so I think we are at time. So I just want to wrap up by just covering a few things, that models are not biased by themselves. The roots lie basically because of the bias in data and humans. Focus should be on building robust and explainable models for critical systems. Explainability is not necessary for all machine learning systems. If it's a mission critical system or a customer facing system, you need to have explainability ingrained in your models. There are other ways to build robust machine learning systems like constraint optimization, adversarial learning. And to ensure that AI progresses in the right direction and is adapted across industries at scale, we need to make sure that we have responsible AI principles in each and every company which is building these kind of models. And that brings an end to today's session. Hopefully, I was able to give some direction to all of you. As you know, like these are really heavy topics, but hopefully some essentials and some of the key concepts is what you get to take away from this. And the whole idea for you now is that you have some direction in the journey as to how you can dive deeper into each of these techniques, be it LIME, be it SHAP, be it implementing some of these techniques and understanding the results from some of these techniques. Feel free to connect with me in case you want to reach out and you have any more questions. And yeah, Chanukya, I don't know if you have time for a couple of questions, but yeah, sorry, it was a heavy topic. I tried to squeeze as much possible in this 1.5 hours.
Yeah, I mean, I think the session was just amazing and very insightful, very exhaustive. Went through all the topics. Thanks a lot, Dipanjan, for such an insightful session. Probably, like, we'll pick a few questions from the chat. So first one is, ensemble models are a combination of many models. So what
Yes.
what exactly is the requirement of local interpretability, like variable importance plots, when global
Yes.
interpretability might make more sense?
Yeah, global interpretability will make sense anytime when if you are using the base feature importance of an ensemble model, it will be based on averaged out Gini coefficients across each and every one of your decision trees, right? So if you are able to explain that to the business, that is great. But in case of the linear approximation, the best part about it is you don't need to know the underlying math behind your black box model, behind your ensemble model. All you care about is the predictions being made by that model and the input features, and then you're trying to fit a local model around a neighborhood. So in that case, all you're trying to do is you're trying to generate a local approximation, which is a linear model, by the way. It is not like a non-linear model there. So you're taking a neighborhood and generating a local approximation model, and you're trying to explain the decisions made by your underlying black box model. So there are no inherent assumptions for an ensemble model because we treat an ensemble model just like a neural network model. We only care about the predictions from that model and the base features, and we fit a linear model on top of a local neighborhood. And in case of SHAP, the difference is that there is no like a local neighborhood similar to LIME, but we just consider each and every one of the features. We consider a coalition of the features by doing the permutations and combinations, and we look at how it's affecting the model prediction probability. And by model prediction probability, I mean the underlying black box model. So yeah.
Right. Yeah. And someone asked, I mean, this was early on, what is model objective function? Maybe if you can, you already covered, but probably like if you can throw light on it a
Yeah,
bit.
so like a simple way could be like a simple, let's say one is when you try to minimize, one is your loss function, where let's say if you're trying to optimize a linear regression model, you will optimize on the sum of the squared errors. So that's where you take your actuals and your predictions, and then you do a basically sum of the squares of the errors, and then you try to optimize it using gradient descent. So basically minimizing something like that ends up being your function, your loss function or your objective function, which you're trying to optimize on for your underlying machine learning model. Yeah.
Right. And we have another question. If we use dimensionality reduction on our data set, will it still be interpreted by using these techniques?
The challenge will become obviously that no, if you are using a dimension reduction technique like PCA, of course you can visualize things, and what you can do is it will be slightly tougher for you to do, but you can, let's say you visualize in 2 dimensions using principal component 1 and 2, you can do a reverse transform, and you can say that features A, C, and D are contributing the most to principal component 1, and let's say features E, F, and Z are contributing to principal component 2. And then you can show the pattern in a 2-dimensional plot and explain it, but it will become harder to explain. But if you do maybe feature selection, you can explain things in a better way using techniques like this. But if you go for raw EDA and you want to explain using dimension reduction, that is the only way, where you have to do a reverse transform and explain which are the base features contributing most to each of those principal components.
Got it. Yeah. And how to use SHAP for unsupervised models?
Okay, so unsupervised models become tougher because that is where you don't have like a specific target function which you're trying to optimize on. So that is where I'm pretty sure some work must be going on. I honestly haven't used SHAP on unsupervised like clustering models and so on, but what we usually try to do for clustering is something I will say is when we build a clustering model, we will try to generate the clusters, and then we will try to look at some features, and we will try to look at distributions, right? Like what is the average price in terms of people spending in customer segment 1 versus 2 versus 3, what is the box plot, and then we try to pick the most influential customer segment. So that is something I do, but SHAP or Lime is something I've definitely not used for clustering models or unsupervised models. Yeah.
Got it. And so you have used emoji is constant in combination. Any reason for it? I think somewhere in the slides you have used it. In SHAP, my local model prediction for an instance is 0. But
Yeah, if you're
yeah,
considering this, so yeah, this is just an example given by Christopher in his book. That is the reason I have used it, no particular reason. So if you want,
yeah,
you can always remove it. But
yeah.
yeah, I mean, let's say here it is just showing some variations. You could also check the effect of if the emoji is not present and the probability is given by the model. Most probably it will not be that influential. But yeah, I mean, you can always consider that as a feature if you want to. Yeah.
Got it. And what is the blue arrow in reverse direction in the diagram of Shapley values?
So that is basically what is driving the model to predict things in a negative way, which means prices are going down, or in this case, basically the gain, which is, as I discussed before, right? In SHAP, we are trying to explain this gain. So what is causing a reduction in this gain, basically? So that is what is the blue arrows, which is trying to explain that how is the prediction decision, or which are the features which are affecting the prediction decision in a negative manner.
Got it. Yeah. Thanks a lot, Dipanjan. I think the session was really insightful, and I think we are pretty much done with the queries. But the rest of the queries, I think they're pretty much addressed or covered in some of the
Yeah,
topics.
sure. Thanks a lot. Yeah,
Yeah,
I know
yeah,
like this is a heavy topic, so I
yeah,
I had to keep a bit of pace. So I
yeah,
apologize if I was going a bit fast, but sadly, as you know, the main intent was to get people to know what are the techniques out there, know some essentials, and now you can always deep dive. There are a lot of references out there. I will share the slide deck with you also, Chanukya,
yeah,
and you
yeah,
can
yeah.
share
Yeah,
it out
that's
across with all the people. Yeah.
Yeah, yeah, sure, sure. Definitely, that will definitely help. And a lot of people are asking for that, and a lot of thanks are pouring in. Thanks a lot, Dipanjan. And any suggestions on like how to approach this? I mean, have you applied in the industry so far, or like any things that you? I'm sure like this is a very nice session to get started, but when it comes to industry applications, what are your general thoughts or suggestions on this?
Yes, so if you're looking at machine learning models, I will advise to not use Lime if possible, because if you change the neighborhood, we have seen that the prediction decisions completely change. So, I mean, the importances which the model gives. So, the neighborhood is a real critical factor. So, that is where I would advise to use SHAP, because imagine like you're running a notebook and you are showing someone the example of Lime, and you run it the next time the example importances change. So then the whole point of XAI is lost, right? It is not transparent anymore. It's not reproducible. So that is where I would advise either use a neighborhood which you have tuned on, which is giving you consistent results, or focus more on SHAP. And SHAP works pretty well. We have used it for a lot of use cases, and it gives pretty decent results. It is reproducible. That is the best part of it. The problem with SHAP, though, is it is not very scalable. I mean, it is scalable than base Shapley, obviously, because it does a lot of optimizations under the hood. So I would say this is still a work in progress. This area, if you look at the Gartner trends, also like this is something which is like not completely mature yet. So I'm pretty sure we will see more scalable techniques in the future. But if people want to use XAI on machine learning models, I would advise to go for SHAP. It works pretty well. And if people want to go for deep learning models like images, they can go for usually your GradCam. GradCam works pretty well. We have used it a lot on a wide variety of use cases, so I would definitely recommend to check that out. And if people are interested, I mean, we can always do a more advanced session on that. But these are some definite techniques which people can use. And in terms of learning, I would say that Christopher's book is pretty good, Interpretable Machine Learning. Do check it out. It has a lot of these concepts which we just talked about, and you can start from there. You can learn through examples. I think that is the best way. Like as I showed these examples here, right? You learn how these examples are working, and then you go and check out the math behind the scenes, and it will become easier for you to understand. So yes, do check out this book. I have an article linked here also, where I have written a couple of articles on model interpretation. So do go through them when you get some time, and that will give you a kickstart, and then you can expand and try out different packages. In terms of packages, the SHAP package is good. Interpret ML from Microsoft is also pretty good. So these are two packages I would recommend in general.
Nice. Yeah, thanks a lot, Dipanjan, and
Yeah,
thanks a lot to all the folks out there for being such an amazing audience. Thank you, and
yeah.
yeah.
Thanks a lot, everyone. Yeah.